The far side of the moon exists in absolute radio silence. Because it never faces Earth, sending a spacecraft here means an endless communication blackout. Yet resting in the shadowed basin of the Apollo crater sits the Chang'e 6 lander. Bringing physical pieces of the moon back to Earth is intensely difficult. After the Soviet Union's Luna 24 mission returned with a few ounces of lunar soil in 1976, deep space exploration experienced a massive drought. For 44 years, no country successfully retrieved a single lunar sample. That historical vacuum prompted the creation of the Chinese Lunar Exploration Program, officially known as Zhangguo Tanwei Gongcheng. The project's spacecraft share a namesake, Chang'e, moon goddess of Chinese mythology. Approved in 2004, the program operated on a strictly defined three-step architectural strategy. Step 1, orbit the moon. Step 2, soft land on the surface. Step 3, return with samples. Rather than aiming for a single, sudden breakthrough, this roadmap relies on a disciplined progression of engineering milestones, building the specific technical foundation required for a long-term lunar presence. Landing and returning a spacecraft requires a multi-module stack. An orbiter, a lander, an ascender, and a re-entry capsule all have to fly together. To loft that much mass into space, China had to master heavy-lift rocketry, resulting in the Long March 5. The Long March 5, or CZ-5, is built around a massive 5-meter core. It utilizes high-performance cryogenic propellants, super-chilled liquid oxygen and liquid hydrogen, which provide massive thrust while remaining non-toxic. This propulsion system gives the Long March 5 the power to deliver 14,000 kilograms of payload directly into a geostationary transfer orbit, a high-altitude path that slingshots the heavy Chang'e hardware toward the moon. Without overcoming the brutal physics of escaping Earth's gravity with maximum tonnage, the subsequent deep space ambitions would have remained permanently grounded. But mass wasn't the only obstacle. The moon is tidally locked, meaning its rotational period matches its orbit. The same side always faces us. If you land on the far side, the mass of the moon itself physically blocks all direct radio signals back to Earth. This diagram illustrates the Keqiao relay network, a satellite placed in a stable halo orbit behind the moon, bouncing signals down to the far side. Later, Keqiao 2 utilized a frozen elliptical orbit over the South Pole, providing higher transmission rates. Establishing this relay network solved the geometry problem of the tidally locked moon, enabling continuous data transmission from a region that had previously been a complete communications dead zone. Once communication was secured, the hardware had to survive the descent. To safely navigate the jagged, cratered terrain of the lunar surface, the Chang'e 3 and Chang'e 4 landers relied on complex autonomous systems to scan the ground and actively avoid hazards on their way down. Upon landing, they deployed the U-2 rovers. A single lunar night lasts 14 Earth days and drops to freezing temperatures. To keep their solar panels charged and avoid freezing, the rovers had to calculate drive routes to physically follow the light. As they crawled along, they used ground-penetrating radar to map the subsurface geology. Nailing the soft landings and keeping the rovers alive in a hostile environment proved the surface hardware was mature. The program was ready to attempt the final, most complex phase, coming back. The Chang'e 5 and 6 missions were built for sample retrieval. After touching down, a robotic arm deployed a rotary percussive drill, driving 2 meters deep into the lunar regolith to extract pristine, intact core samples. Those samples were sealed inside a small ascent module. Acting as a miniature launch pad, the base of the lander stayed put, while the ascender fired its engines to blast off directly from the lunar surface, flying up to automatically dock with the return orbiter waiting above. This diagram illustrates how the capsule handles the extreme velocity of the journey home. Using a skip re-entry, it dips into Earth's atmosphere, skips off the upper atmosphere to bleed off deep space speed, and plunges safely down to the surface. When the recovery teams reached those charred capsules in Inner Mongolia, they verified the complete end-to-end architecture of the Chang'e program was fully operational. The capsules were transported to the Ground Research Application System in Beijing, where analysis immediately yielded results. Researchers sifting through the near-side samples isolated a brand-new high-pressure mineral formed by ancient asteroid impacts. They named it Chang'e. The far side samples delivered even older data. Scientists dated rock fragments back 4.2 billion years, nearly to the formation of the Earth itself, and confirmed that volcanic lava flowed on the moon's far side for at least 1.4 billion years. By storing these samples and opening applications for international scientists to study them, China transitioned its role from a solo spacefaring nation into a central hub for global lunar research. Now, the program enters Phase 4. The upcoming Chang'e 7 and 8 missions are targeting the lunar South Pole, deploying specific scientific payloads to hunt for water ice trapped in permanently shadowed craters. This technical roadmap outlines the long-term objective. By linking these modular landers, rovers, and communication relays together, China intends to construct the International Lunar Research Station, a permanent, robotic, and eventually crewed scientific base operating in the 2030s. Through 2 decades of methodical, phased engineering, the Chang'e program has taken the moon from a silent, unreachable void and turned it into a connected extension of human infrastructure.